One other form of measurement that we need to discuss in this chapter is density. Now, density is a little bit unusual because it's not a direct measurement. Density, we all know and love as essentially a measurement of how much matter is in a given volume. Now, that's really a combination of two different units of measurement. So the how much matter is really defined as mass, and then in a given volume is, of course, in volume. So mass per volume, or mass divided by volume, is essentially what density is. Now, my main focus here is not to show you how to do a density calculation. You should have been doing those since the junior high. I just want to reinforce a couple simple ideas when we approach density problems. Now, another thing to remember here is that density, because it is a combination of two or more different directly measured units, is itself called a derived unit. So it's a unit made of two other systems of measurement. The equation for density can be simplified to D equals m over v, or density equals mass divided by volume. And depending on what the problem is asking for you to solve for, you may need to algebraically rearrange the equation. So this is the equation that I would use if I was given mass and volume data and asked to solve for density. But other equations will actually ask you to solve for mass, in which case I would multiply the volume over to the density side, making the equation d times v equals m. The third and final variation of this, of course, would be for solving for volume. This equation I would use to solve for mass if I was given density and volume measurements. If I was asked to solve for the volume, however, I would rearrange the equation to equal volume equals mass divided by density. Now, density is a really, really great opportunity for us to practice a couple of things. First of all, scientific measurement. For some reason, when we're thinking about adding, subtracting, multiplying, or dividing two measurements together, for some reason our brains leave our heads and we forget our good practices with scientific measurement. Always take a look at that scale and make sure that you're including not only the certain digits that are on the scale, but also that extra estimated digit and the unit at the end. It can make a ton of difference in the end with the significant figures. And those significant figures can really, really, really cost you, honestly, some percent error points. But again, you really want to make sure that you're taking good time to be paying that special care and attention. Now, another thing that I wanted to make sure that I reviewed with you is that sometimes the volume is a little difficult to obtain. When you're taking the volume of a liquid, it's pretty easy because you can just pour it into a graduated cylinder and then record it. But sometimes we're going to have solids that we need to obtain the volume of. So I wanted to review the method for taking the volume of an irregularly shaped solid, like for example, a rock. So if I had a rock and I need to take the volume, I would first take a graduated cylinder and fill it up part way with water and record that measurement. Then gently slide the rock into the graduated cylinder and record the new volume of that water. The volume distance, not distance, but the volume difference is what the volume that we could attribute to the rock. So again, the starting volume minus the final volume equals the volume of the rock. We call this method the water displacement method for calculating the volume of an irregularly shaped object.